Okay, dear colleagues, let's start our conference. This is the second conference dedicated to the memory of Alexander Ananyin, Sasha Ananyin. He is our friend, teacher, colleague. He was, of course. And maybe Ivan Chesov tell us a couple of words.
Yes, okay. First of all, I'm very happy to see that this conference is running and so many people giving nice talks and participating. So maybe let me just recall some small story that a long time ago, Sasha and I were organized a small workshop in Ilhabela, and our first speaker, Jehun Park, was there. And after the talks, we went with Jehun to work on a beach, because it was conference was basically on a small island next to the beach, but it was so hot in the building. So the only way actually to do some math was on the beach in the shadow of mango trees, and it was some breeze from the ocean. And we was working with Jehun on every afternoon, and from time to time mango fell next to us, and we was like drinking it, and not eating, actually drinking it, because it was over ripped. And Jehun told me, Vanya, this is our best office. And Sasha, basically, he was local organizer, organized this event. It was very nice. We had very good memories from this conference, and I think this is where Jehun met Sasha. It was a long time ago. And it was actually very nice. Sasha actually was very tired after this conference, because he basically did everything. And it was a lot of work. A lot of people came all over the world, also from Brazil, from Europe, from US, from Korea, from Russia. And there was because it was also very hot. It was in winter, so but it was actually weather was very hot. So Sasha actually felt very tired after this. So basically, this is my last memory of Sasha, because since then I only met him on Zoom, but many times, but not in person. Yeah, but I kept this memory alive. So yeah, and we're organizing this volume in Sasha's memory, and many people gonna contribute papers to this vote proceedings. And I'm very happy that this is we keep this memory of Sasha like. For future generations, yeah. And I'm very happy that Jehun is going to be our first speaker, and he will talk about beautiful subject, which also I personally like very much, because it's a continuation of our work with Jehun, which we started long time ago in Korea, and Jehun had a recent breakthrough with our friends, and he will talk about this. So, yeah.
Okay, thank you very much. Thank you very much for the invitation and the introduction. I met, as Vanya said, I met Sasha Ananyin like 8 years ago in the Ilhabela, Brazil. I don't know much about him, but I know he's a very good man. Okay, that's all my memory. All right, so let me start my talk. All right, so I will talk about the factoriality of the double solid. So here is the object. So we consider final threefold with the only terminal singularities in general, but we'll also consider hypersurface of the P4 or like a cyclic cover of P3. So in fact, we're gonna focus on the double cover of P3, which is called the double solid. So in this case, the Picard group of X is the isomorphic to the second integral cohomology of the X, because our H1 of X and H2 of the OX is trivial. So in this case, X is a factorial if and only if the length of the second integral cohomology is the same as the length of the first the integral homology groups. So this is
sort of, do you mean here Q as coefficients?
This
Rank not integral but rational.
In this case, I mean, this is the Z integral case. So rank, if you consider like a Q, then you just consider the dimension of the vector space. Okay, that's the same. So here, so this is usually like on the smooth case. This comes from the dual and the Poincare duality, but in general, this is the duality phase on the singular varieties in general. I mean, so this failure of the duality measured by the difference of this two numbers. I mean, the rank of the first integral homology. I mean, homology and this rank of the second like a homology groups. So this difference is called the defect of the X. Okay. So as I said in this talk, we consider double solid. That means the double cover of the P3 branched along the surface B in P3 of the degree 2R with only isolated singularities. You may consider this double cover as the hypersurface in this weighted project space 1, 1, 1, 1 R. Okay, with the as the hypersurface of degree 2R. Okay. So this singular points on X may have an effect on the integral homology or the homology groups of the X. But we have the still Lipschitz type theorem, so you can see this the Picard group X is the same as the Picard group of the ambient space, this P. So that means the rank of the Picard group of X is just 1. Okay. So, and one remark is that the long time ago Gamata proved that on Gorenstein terminal 3-4 case, factorial is the same as the Q factorial. So let me just say the Q instead of the Q factorial, so we can talk about the factorial varieties. So if X is a factor, I mean the X is the factorial in our case, if and only if our defect is the trivial. This number is the trivial. The difference between the rank of the fourth homology groups and the rank of the second homology group of X. If they are the same, then X is a factorial. So, but the problem is that it's not simple to compute this number defect in general. But like Clemens in 1983, he provided a beautiful formula about the defect. I mean, how to compute the defect in the case our double solid had the nodal singularities only. So the formulas are developed for the hypersurface cases, and then so that was the 1990 node case, and Sink and the RAMS recently, not recently, like 10 years ago, they improved this formula to the ADE singularity case. So ADE singularity means you have this type of the equation for the singularities. So this is the normal form of the like a Dubois singularity on the surface, and then you have the extra, and because this is 3/4, you have one more variable with the square, and this is the higher order terms. If singularity can be expressed in this way, I mean, as a hypersurface singularity, then we say this is the ADE singularities. So in this talk, we only consider the double solid with this ADE singularities. Okay. So this ADE singularities is the isolated singularity, and moreover is so-called the absolute isolated singularity. So you can reserve this singularities only by blobs. I mean the blob at points, the close points. So you can have that means you can have this big resolution. So it's something like this. So it's the big resolution is like this. So it's composed of the blow ups of the close points. So like this, and at the end you have this smooth point. Okay, this is so each guys is the blow up with the center of the isolated singularity of this threefold. So this is called the big resolution. Okay. All right. So for some technical purpose, we define some transformation. So you have, so here I have this blow up. So one of this, something like this. Okay. All right, and suppose you have diverge H here, then I will denote by script S, small s, J of H, which is denoted by this pullback of the H minus this exceptional divisor of the blow up. Okay. All right, just the notation. All right, and this, I said this 4 people, like Clemens, Dimka, Sink, Rams, they developed this formula. So here we have our double solid here, and there we have this big resolution Y. And then like they provide this formula for the H11 of the Y. Okay, so this is given by thus. All right, so here this is one form. I mean, this shift is defined by this, like this iota is just the embedding of this singular locus into the P. Then you push this shift one form, I mean the shift of one form, I mean on the smooth locus to this P, and then you take this H1. Actually, this is the same as the length of the Picard group of the P, I mean our ambient space, so it's gonna be just the 1 in our case. All right, and this is the number of the components of the exceptional locus of our big resolution. Okay, and this is our defect. So that this formula gives us the H11 of the Y. Okay, this is actually the length of the Picard group of the Y and the length of the integral homology group of the Y. Because the Y is the smooth, and then you have this Poincare dual. So these numbers for the Picard number and the numbers of the force homology groups, rank of the force homology groups are the same. Okay. All right, let's take a look. So how to compute these numbers? We know this is the 1 and this. Let's take a look at this number of the exceptional components. So we have this situation. And this is our P3, and this is our double curve X, and this is our French locus. This is a surface of the degree 2R. All right. Here, I'm gonna put the one more restriction. So we suppose this B has only like AN singularities. So this, in our case, this is equivalent to the fact that the X has only a CA1 singularities. This is the same in our case. So this is a CA1 case. I mean CA1 singularities is the ADE singularities. All right, so now, as I said, we assume that this X has the only CA1 singularities. That means B has only like AN singularities, cyclic type of the Duval singularities. So let's say B has this many and this type of the cyclic Duval singularities. This is the number of the A1 singularities on B, and this is the M2 is the number of A2 singularities. So this is the non-negative number, and this or this singular points of the type AJ. Okay, all right. Then each AN singularities can be resolved by this many times resolution. So you're gonna have this many like exceptional divisors. In this case, if B has this type of singularities, then this mu x, number of the exceptional divisors, can be defined by this. Okay. All right. All right, and let's talk about the defects. So this is the duty at Sink and Rams. What they proved here is the following. So they first define that this space, this vector space. All right, so you consider like this hypersurface in P, which satisfies this following conditions. So first, H contains the all singular points of the X, and then like you take this like a transformation which I defined before. This one. Okay, each step when you have the divisor. This one defined by the pullback of the divisor minus exceptional divisor. Okay. All right, and then you perform this transformation until J with this. And then you check whether this singularity is contained in this here. Then you collect the all H here, hypersurface, which satisfy these two conditions. Okay. All right. Then it turned out to be this defect known to be a dimension of this guy. Dimension of this guy, this space, minus the original space here, and the plus this number of the exceptional divisors right here. All right. But this is all right. So this is this. Let me add more. So here our X is hypersurface in here, which is weighted projective space. This is the 1, 1, 1, 1 R. Okay, this is the degree 2R. So you consider hypersurface in this. This is the threefold hypersurface here, and then you collect the all hypersurface which satisfies this condition. Okay. Actually, this is the this degree has the 3R minus 4. X is the 2R. This is the 4R divisor, and this is the minus 4 minus R. So this is this. So in this weighted project space, you collect the two. To make this the vector space, you collect the hypersurface of the degree 3R minus 4, which satisfies this condition. Okay. All right. But in our case, this is our case is a double cover P3, and let me emphasize our situation. So X is the double cover P3 ramified, branched along the B, surface B. So instead of the this three-dimensional hypersurface, you can just the two-dimensional. You can consider two-dimensional hypersurface. It's the same. The region is simple, but I don't want to explain. Because I don't have enough time. So instead of the three-fourth hypersurface, you consider like this two-dimensional hypersurface in P3, degree 3R minus 4, which satisfies this condition. The almost same condition like before. All right. Then this defect can be computed in this way. This is by the Sink and Rams. All right. But this condition is not like it's not simple to check. It's not systematic. So what Rams did is the following. So he translate by the simple, this condition into the simple way. So this is the new, he simplified this condition, previous condition, into this simple, more like a checkable condition. So our space, vector space HX is the hypersurface of P3 degree 3r minus 4, which satisfies the condition A. So condition A is described as follows. So you consider each singular point P in the surface B, this French divisor. All right, then with this singular point, so our B has only cyclic Dubois singularity, so AL type singularities. So you can express the surface locally like this, right? So x1, L plus 1, x2 squared, x3 squares, and the higher order terms around this point P, right? All right, then you see. So this condition just can be introduced, translate into this way. So H of P, the surface passing through this point P, right? So vanishing at P. And the other condition can be like this. So this is our x1, and you take the partial derivative with respect to x1, j times right here. So this is a condition for this condition. Okay. So if this satisfies this condition, then this is the equivalent condition like this. Okay. All right. So this each point P, all right, this is the AL type singularity, right? This is the AL type singularity. Then this AL type, each AL type singularity makes the this many conditions, right? This is one, and each J from the 1 to this number. So you have this many conditions for this. So all together, you vary the all singular points, then you're gonna have the exactly the condition. In this condition A, you're gonna have exactly mu x conditions. So number of conditions in A is the same as the number of the exceptional components. So at this moment, now we can say X is the factorial if and only if this defect is trivial, and if and only if this condition A impose the mu x linearly independent condition on this vector space, right? So a long time ago, like almost 15 years ago, like Vanya and I, we proved this theorem. So if B has only A1 singularities, okay, A1 singularities in this case, and the number of this A1 singularities is strictly less than the R times 2R minus 1, then X is always factorial. Okay. So we use the several statement, but to prove this, we use the several results from the some zero-dimensional scheme theory, but it doesn't require the singularity must be A1 singularities. We just check whether some surface passing through this point or not, or those kind of things. So here, if you look at this condition, if instead of so in A1 singularity case, you don't have this condition. You don't have this condition at all, A1, because this number is 0. So you just check this H pass through their point or not. Okay. And if you have A2 singularity, you don't have this condition, same. All right, this number is 0. So you just check for the A2 singularity case also, you just check this H pass through the point or not. That's it. All right. For this reason, so you can generalize, we can immediately generalize this statement like this. If suppose B has only A1 or like A2 singularities, then this statement holds. Right?
So for quartic double solid, it will be 28. Yes.
Quartic double solid what?
So if R is equal to
This number?
4, yeah.
This number is what? R is 2.
Times,
So,
so 40.
this is 5. Yeah, 6. We talk about 6 in this case.
So for quartic double solid, R is equal to 2, not 2.
Yeah, 2.
4?
R is 2.
2. Thank you.
All right, so let me give you some key examples which motivate our study in this area. All right, so this is the first key example. So you consider this sextic double solid. So you have the F in the variable X, Y, Z, W, and you have the this. But you take the square, and here this is actually the branched surface, right? And then you have this double. Okay, so here our X here and P3 here, and our B, this branch divisor, which is defined by this equation, 2R minus 1. So this is the degree R, the R polynomial, homogeneous polynomial, and G is the degree 2R minus 1, right? All right, and so here we consider the hyperplane section H by W. Then you see, if you look at the formula carefully, so you don't have you put the 0 instead of the W, then this equation will be split in 2 parts. So W equal to 0 and this guy 0, and W equal to 0 and this guy is the 0. So when you take the hyperplane section by W, this means that you have the 2 components, D1 and D2. D1 is the this and the D2 is the this, right? But the Lefschetz the Lefschetz term still holds for this case. So Picard group X is generated by this hyperplane section. So which means D1 and D2 cannot be because this guy cannot be generated by H. This means that D1 and D2 is not Cartier. So that implies that this double solid is not the Q factorial. Okay, all right, let me give you a second example. All right, in this case, so you consider smooth threefold in P1 cross P3. You can in P1 cross P3, you consider smooth threefold of by degree 2R, where R is the the 2, which is defined by this way. So U, V is the coordinate for the P1 and X, Y, Z, W is for the this P3. And here FR and HR, GR is the general homogeneous polynomial of degree R. Okay. All right. And you have this natural projection to P3, right? Then when FR and the HR, GR vanishes, then the common solution defines the the R squared curves in V, contract to the point P3. Okay. So in this case, we consider Stein factorization. So this is the original map, and you have this Stein factorization. All right, then this phi contract this all curve CIs. Okay, and this gonna be a small morphism of V to X. And this X to P3 is exactly a 2-to-1 map, and the branched along this. This is the discriminant of this quadratic equation with respect to U V, right? So this is our French locus for this 2-to-1 map. All right, but this phi is the small morphism of V onto X. So that means X cannot be a factorial. So this is the Q factorial. Okay. Okay, and here I didn't use any like singularity types actually. So you may consider this. So here I more consider like I consider more specialized case. So here my FR has the only variable X, Y, Z, and here I have instead of here H. Instead of H, I just put the W to the R's, okay? W to the R's, okay? And here, instead of GR, I used only X, Y, Z here. And in this case, we're gonna have this R squared curves contract to the 2 points on P3. And using the same argument, you can see this guy is not Q factorial. So in this case, so previous case, if you consider this guy is general, then this will have the only A1 singularities, R cubed A1 singularities. But in this case, we have R squared A2R minus 1 type singularities here, because we have this term here. Okay. So as before, this is not Q factorial. Okay. All right, and let me explain why this is not Q factorial from the point of view of the RAMs. So let me remind you of Kelly-Bach-Haraka theorem for plane curves. So C1, C2, C1, C2 plane curves of the degrees D1 and D2, okay? And let's suppose, for simplicity, these two curves intersect D1 times D2 distinct points on the plane. Then Kelly-Bach-Haraka theorem tells us that this D1, D2 points impose the dependent condition on this space. The set of hypersurface of degree D1, not set of the plane curves degree D1 plus D2 minus 3. Okay, this is the classical Kelly-Bach-Haraka theorem. All right, so our B was this, right? W2R plus FR times GR. So as I said, this has the R cubed A2R minus 1 singularities. All right, then you consider this condition. In condition A, you have this condition in this case. So that means you take the partial derivative with respect to the W, R minus 1 times here, and you require H to be a 0 here. You require H to satisfy this condition. So it's about this term, this type of the term. So you must have this term, and this is about this, and this is the curve of the degree 2R minus 3 here, and our R squared point on here, FR and GR vanished in here. So this is the R squared condition on this vector space. So that means Kelly-Bach-Haraka theorem. So by Kelly-Bach-Haraka theorem, so you have the linearly dependent condition. in this condition A. So that implies that your defect is strictly not trivial. So at least one, so that means X is not factorial. So we can produce many examples like this. Let me give you two examples, two more examples. Okay, so let's consider this type of like hypersurface. I mean the double cover of P3. So in this case, our surface B has exactly 2r minus 1, 2r minus 1 singularity points. In this case, right? This singular points come on this plane defined by W equal to 0, and you have the line and this 2r minus 1 curve, and they intersect the 2r minus 1 points that makes this 2r minus 1 2r minus 1 singularities here. So by same argument as before, I mean this Cayley-Bakkeracka type argument, you can say this is the independent condition on here. Or you just take this hyperplane by X, and then you argue with your Alexis hyperplane term. So then you have this hyperplane. You can find this hyperplane with your two components, which violate the Alexis term. That means this is the not Q factorial double solid. So here, in this example, we keep in mind this number 2r minus 1 with the 2r minus 1 singularity types. Okay. All right, and I give you one sextic surface in P3 with the this is our B in here, and this guy has the A11 singularity at this point and A1 singularity at this point. Okay. All right, so you have this double solid branched along the surface. All right, and then you check this Ram's condition, then you can immediately see this condition implies this guy vanishing at P implies this guy vanishing at Q, which means our condition A is not linearly independent condition. That implies this is not Q factorial. Okay, so here we have A11 singularities. A11 singularities. So based on this fifth example and the sixth example, I made some conjecture, which actually, to be honest, I'm not sure whether this is the good conjecture or not. I mean, I'm not sure I'm not sure this is correct or not. But I checked with a small number. It looks fine, but as at the beginning as I write, it said this is the preliminary report. So as for this conjecture, I'm not sure about this conjecture, but at least my example tell me this. So we consider a double solid. Conjecture is this. So you consider a double solid branched along the surface of degree 2r with the m most am singularities, and this m bounded by this 6r minus 8, and number of singular points is strictly less than the 2r minus 1, then x is factorial. Okay, this is my brave conjecture, and I checked with the quartic. It looks fine. I mean, this case is simple. So this number is just a 4. Okay, so R is 2, so you have 4 here, and number of singular points is at most 2. So you can easily check, play with the 2 points, singular points. Yeah. But if you consider this sexic double solid case, so your singularity types up to 10. So you allow the A10 singularity. You see, in the previous example, we have A11 singularity and the non-Q factorial case. And you have here, in this case, we have the only A10 singularities at worst, and number of singularities, the maximum number is the 4. So you play with, but still, I cannot check. So you see, like this Duval singularity types on the cubic surface is completely classified, and the Duval singularity types on the quartic surface is completely classified. But sextic double solid, we don't know. We don't have much information on it. And moreover, like it's very complicated. So I mean, even though like the numbers are small. So what I did is the following: this conjecture for sexic double solid is a holds, I mean the true for with the following extra conditions. So B allows A6 singularities at worst. The original conjecture says A10, okay? And I have some like some geometric conditions, like node 3 of the singular points of B lies on the single line, and this is a strange condition. Then I can prove that this wild conjecture is the true. But I need more time to understand this phenomenon. So I think my time's up. So more or less, let me stop here. Thank you.
Okay, thank you very much. Let's thanks to our speaker. Are there any questions?
So maybe one small question. If you consider this double covariance, so there are two fun ones, sextic double solid and quartic double solid, yes?
Yes.
And for quartic double solid, there is a statement that non-Q factoriality implies rationality. For non-nodal ones, yeah, maybe. Only with A1 singularities or something like this.
I'm not sure. I'm not sure the non-Q factoriality implies the rationality in quartic case. Is it true?
So as I remember, maybe Vanya can correct me. As I remember, for quartic double solid, it's like this.
For sextic case, it's not true. So I mean, at least for sextic case, there is the example non-Q factorial irrational case, and also non-Q factorial rational case.
Mm-hmm.
But
even with only nodal singularities, yes.
Yeah.
So
not sure. So what we can say is like this: Q factorial with the nodal singularity implies the non-rationality, but the other with the other condition, I'm not sure.
Thank you.
Okay, thank you very much. Are there any other questions? Okay, I don't see. Okay, thank you very much again.
All right, thank you.
Our next speaker is Misha Verbitsky.
I hope, do you hear me?
Yes.
So I will share screen and try to, well, share. The problem is that in Brazil, everybody uses Google Meet. So I'm slightly out of how to share a particular window and not the whole screen. Is it actually possible or what?
Миш, ты нажми просто делиться экраном, и там будет выбор нескольких окон, ты выбираешь.
Understood, thanks. Share. No way. I'm sharing my screen, right?
Right. Yeah.
Может, это на Windows, у тебя же не Windows.
Yeah, I have Linux.
О,
Anyway,
теперь видно.
what I can do is, but then I won't see anything. I can just put this screen to the whole. How to do it? Just make it the whole screen and hope it will be sufficient. But I don't see. So do you see what the non-commutative quasimorphism stuff? So
Yes, we see.
good. So I assume it works. Excellent. Thank you very much for it's a great conference, and I'm grateful for the invitation. I will be speaking on a joint work with Misha Brendenbursky from Beersheba, and he comes from geometric group theory and symplectic geometry, and my point of view was more hyperbolic. In fact, it was part of the idea was shared with Sasha Ananьina, who was always very interested in how you can work algebraically with hyperbolic structures, like hyperbolic groups, hyperbolic spaces. His main subject last years was hyperbolic spaces fibered over a disk with a fiber which is a disk. Oh, sorry, over a Riemann surface with fiber which is a disk. So, and I always told him that he should consider variation of Hodge structures and approach which was pioneered by Hitchin and Simpson. I'm not sure if it would help him or not, but it definitely was my motivation. So there are some now currently approaches how you can go from algebraic geometric point of view with variation of Hodge structures, Higgs bundles to just group theory. The first problem which occurs is that we don't have bundles with connection. We have only representations which are flat bundles. And this is our point, our idea how to approach this construction. So instead of representation, we'll consider approximate representations. So this is the first definition, which is very classical. It is due to, well, it was a question of Ulam. Ulam asked him, and by Ulam in his book in 60s, book on geometry questions and algebra questions. I think it was questions on geometry and algebra or something. And then Thurston and Hirsch had a formal definition of quasimorphism, and Gromov was the main driver of the early notion. So what is a quasimorphism? It's a map from a group to a group, which is approximately a homomorphism. So the second group should have a topology. And then what we have is that the defect, the difference between homomorphism and non-homomorphism. So you have Q of xy, Q of y minus 1, Q of x minus 1. It is a defect of the map. It should belong to a compact. There are several versions, which are equivalent for commutative group and non-equivalent for non-commutative. I will skip it. So this was the Ulam notion. He did it for a map from a group to itself, though, but he had this. And of course, you can also define equivalence. Two quasimorphs are equivalent if they map. Again, the difference between these two maps is bounded, belongs to a compact, and people consider quasimorphisms with commutative target, with R, mapping to R, and from geometric point of view, it's the same as aligned bundles, which is interesting, but completely devoid of all of every geometry-like variation of such structure.
Sorry, I have a question. And so we
Please.
fixed compact subset is for all quasimorphisms and or for every quasimorphisms new compact subset.
Yeah, for every quasimorphism, there's a new common size. So we wanted to be bounded universally in the group, but of course, it can be just an open ball if you have a method.
Okay, thank you.
Or sometimes the group is countable, like discrete, and then it's finite set. Okay, so the example, this is the first example. I will give a couple more examples, is Poincare rotation. So it's as usual, you have the group of diffeomorphisms of anything is usually perfect. It is coincides with this commutator. So there is no homomorphism to R, but there is approximate homomorphisms like Poincare. And in fact, once this at least the symplectic motivation for that is that the same is true for a group of Hamiltonian diffeomorphisms of a symplectic manifold. This is a group which is perfect. There's no homomorphism to R, but its commutator length is infinite, meaning that if you have an element, you can decompose it into a product of commutators, but not finally, not bounded many. And this gives you lots of interesting geometric structure related to quantum cohomology. In fact, you can describe like idempotence in quantum cohomology in terms of quasimorphisms on the group of quantum of Hamiltonian diffeomorphisms. This was the symplectic motivation and something we're going to reach it hopefully in the future. But for them, it's always commutative. So the group is commutative. There is another motivation, which was original Gromov's idea, which related to bounded cohomology. I won't spend much time on it. I will just show you briefly the slide. So you can have singular complex or cellular complex for topological space, and then the cohomology is functionals, the linear functions of this complex. Okay. The complex has a basis because it's a free groups or frees or like projective vector spaces. It has a basis, and let's consider bounded functionals on this basis. So we put a norm related, L1 norm related to this basis, and we consider bounded functionals, and the result is called bounded cohomology. The funny thing about bounded cohomology is that it doesn't care about the space at all. It cares only about the fundamental group. So if it's simply connected, bounded cohomology are zero. If it's and generally it's just invariant of P1. And of course, then it means that bounded cohomology of a group is just bounded cohomology of its classifying space, Ellenberg-MacLane space. Okay. And then you have this following exact sequence. You put quasimorphisms inside quasimorphism to R. It should be an R row here. So you have homology mapped into quasimorphism. Cohomology are just homomorphisms to R. So it's mapped to quasimorphisms. Quasimorphisms are interested up to equivalence, of course. Then quasimorphisms are mapped to bounded cohomology, and bounded cohomology are mapped to cohomology. And the kernel is our quasimorphism space. Another motivation comes from stable commutator length. I already mentioned it briefly. So group is perfect if it's equal to its commutator. The typical example is the diffeomorphism group. Then, and there are lots of interesting quasimorphisms on the diffeomorphism group or Hamiltonian diffeomorphisms, which encode geometry of the manifold in a very interesting ways. So you define commutator length, just how many commutators you need to make G as a product of these commutators. Stable, you take the same with power of G and divide it by you take commutator length from G and divide it by N and take limit, upper limit if you need. This is commutator length, a stable commutator length. There's a whole book, very good one, called SCL by Danny Caligari. And it's a whole huge subject on geometry. And then, and if you have a perfect group, element has non-zero stable commutator length if and only if there exists a homogeneous quasimorphism from the group to R, not vanishing from this element. And then, if you like Gromov hyperbolic group, you can do a lot of things with essentially pretty much all what we know about Gromov hyperbolic groups is encoded into their quasimorphisms. So you can prove theorems using quasimorphisms, or you can just interpret theorems into theorems and so on. Anyway, so before I go into further, let me do some very elementary stuff, which is funny because it originates, it's cut geometry due to Gromov, but it's Katan Alexander Topanogov, so it originates in Novosibirsk. And I'm giving a proof of Katan Adamar, which is slightly different from the usual one. It comes from cut geometry from book of Buraga Ivanov. So the theorem says that if you have a complete, simply connected Riemannian manifold non-positive sectional curvature, then M is contactable. And the idea is you use comparison theorems. So there's certain inequalities between triangles or length of, well, between length of the distance functions on triangles in your manifold and then in a model hyperbolic space. So the important statement for us is that the distance function between, if you have two geodesic segments, the distance function between these two geodesic segments is convex as a function of on a square. And this, first, this implies that any 2 points are connected by unique geodesic, because if you have 2 points connected by 2 geodesics, then you would have distance between the middle points of these geodesics bigger than distance between the ends, which contradicts convexity. And second, you can move along geodesic. And using convexity, this contraction along geodesic, like you can think of it as homotopy, but it's not, it's homotopy on an Euclidean space. Generally, it's just contraction on constant rate along all geodesics, going from a given point to your reference point. This map is a deformational retract. It's continuous and it retracts your manifold to a point, so it's contactable. This is a textbook, except the proof is slightly more general because you don't need to do any differential geometry. Okay. Why do I need it? Because I wanted to state another theorem of Gromov. So we take a reference point and a geodesic interval. And we started contracting using this contraction map. We contract this interval to this point. We obtain a triangle with 3 geodesic ends. It's formed by geodesics parallel in Euclidean case. So you take a geodesic, you contract it slightly towards the origin, and you take the union of all these geodesics. It's a 2-dimensional shape, which on the manifolds, it's actually smooth. So it's called straight geodesic triangle, and its area is bounded. This is what I need, why I did need this Cartan-Adamar. So its area is bounded by universal constant, which is related to curvature, which is something that people who know like Lobachevsky geometry know. All triangles in Lobachevsky in Poincaré plane have bounded length of bounded area of the same, precisely the same. It's pi, or pi times square of the curvature. Okay. And this is used to obtain the model quasimorphisms, which are due to a work of Barge and Gis. So if you have one form, this again classical, this is not related to what we did, but it is. So if you have, it's quasimorphism taking values in R, not in non-conductive group. So you have in one form. And you can, starting with the element of the fundamental group, you can represent this element by a loop and integrate this one form over a loop. If the one form is closed, then this integral is independent from the loop. Because of, independent from loop in its homotopy type. But of course, if it's not closed, then it depends. So we choose a geodesic loop. We choose a geodesic going from, it's unique by Katana-Dama, if we are on negative curvature. So we start with a manifold of complex manifold strictly negative curvature. We take one form and we integrate this one form over the geodesic loop in a given homotopy class of loops. This gives a map from fundamental group to R. And the claim is that it is a quasimorphism. And the proof is very simple. So you have, so what is our defect? So we have three geodesics on the universal cover. One represents A, another represents B, and the third represents AB. Or AB minus 1, which is better. And then on the universal cover, the geodesics form at a triangle. Because on the universal cover, by homotopy lifting, if you lift two homotopy paths, homotopy equivalent paths, they lift to the same end. So this defect is in fact obtained by integration of the one form over a geodesic triangle. And the geodesic triangle over the boundary of geodesic triangle. But geodesic triangle have a bounded area. So if we, by Stokes-Lemon formula, integral of theta over its boundary, the same as integral of its differential over this triangle, two-dimensional. Its area is bounded, and the form should be theta. The d theta is bounded, has bounded norm because it comes from a compact. Of course, we do this integration upstairs, but we could do it downstairs, or we can do it upstairs. It's just bounded norm. So we have a two form with a bounded norm, which we integrate over a triangle of a bounded area. This is the defect of the map. This is the difference between. This is how far this map is from a homomorphism, and this difference is bounded. So this is why we have a quasimorphism. It's a map from a group of our strictly negative sectional curvature manifold to R, which has bounded defect. So this quantity, which expresses how far this map is from a homomorphism, is bound. I would really appreciate asking questions. So if you can ask. Okay. I'm going to do the same with the vector bundles and connections. The Ambrose-Zinger theorem, so first, what is a holonomy? Holonomy, it's similar to monodromy. So if you have a flat bundle, flat local system, you can go along a path and you can start with a frame, bring it on the path to the end. This is monodromy of a flat connection. If you have non-flat, you can start with a frame and you can drag it along a path using the connection, like make a parallel frame along a path. This is called holonomy of connection along a path. The holonomy group is a group generated by all holonomies for all paths. Of course, when connections were flat, this is monodromy of the local system, so it's a discrete group. When connection is non-flat, this group has some discrete part and this group has some continuous part, and Ambros Zinger told us that continuous part is a Lie group. Moreover, it's generated by curvature terms which are expressed with curvature. Okay, this was classical Ambros Zinger. Effective version is, suppose you have now a path which is a boundary of a disk. Can we express the holonomy of this connection along this path in terms of the curvature restricted to a disk? And the answer, yes, we can. So now the theorem, which is lemma, we have a compact manifold of negative sectional curvature, geodesic and polygon, or just triangle, doesn't matter. But it should be, it's a contractible loop of non-geodesic segments. And we have a principal G-band, the connection on, with connection on M. Or if you don't like G-bundles, just think of vector bundles with connection. And now I define holonomy along the boundary of this polygon. Then this holonomy belongs to a compact, which depends on number n. And of course, it depends on the manifold and connection, but is independent from the choice of a polygon. So the proof, of course, you can split your polygon onto, since it's homotopy to 0, you can use Cartan-Adamar again and fill it with straight triangles, and then you can reduce it into triangles. So we prove it for triangles, it's enough. And to prove it for triangles, the area of a triangle is bounded by this previous theorem, theorem 1, and the absolute value of curvature is also bounded because M is compact. So the curvature is on the universal cover is bounded by this. It has bounded norm, and the holonomy is obtained by integration of certain terms associated with the curvature over this triangle, over this inside this triangle, over inside this polygon, so it's also bound. In fact, what I told you previously, it's a version of that, but only when the connection, then the bundle is trivial and the connection is one form. Then its curvature is different. Okay, now the main subject, non-commutative boundaries among quasimorphisms. This is the things which should play the role of bundles with connection if we are interested in just trying to figure out what is bundle connection on a group and not on a manifold. Okay, so we have again compact manifold, non-positive sectional, negative sectional curvature, it's an error. We fix a point, and we we represent given class and final group, element of final group by a geodesic, and we integrate. We take holonomy of our connection over this geodesic path. If it's principal G bundle, the result belongs to G. It gives a map from final group to G. And the theorem for negative sectional curvature that this map is again a quasimorphism, but it has non-commutative touch. Okay, so what is the reason it's very much the same as previously. So again, what is the defect? How far this map is from homomorphism? It's again Q of AB, Q of B minus 1, Q of A minus 1. It's holonomy along a contactable geometric rectangle, and this holonomy is bounded. So inside the group, you have a ball. Inside the Lie group, just like ZL, you have a compact ball which contains all these holonomy operators. And of course, for when you have one form, trivial line bundle, and the new connection, which is obtained from old connection plus one form, its curvature is its differential, and then this implies that what we defined is a generalization of classical Bargis business. Okay. So why people don't study this? The main reason is that they studied, but discovered, it was a great paper of Fujiwara and Kapovich, where they discovered it doesn't work. The main difficulty with, why whether in particular sort of wrong was because they considered quasimorphism values in discrete group. They thought, okay, discrete group doesn't work, so it probably doesn't work. So essentially what they proved that, well, Z-value, not their value, but what they proved is that quasimorphisms with values in discrete groups are pretty much the same as homomorphisms and commutative quasimorphisms. They reduced everything. So precisely they did this very strange definition, which takes very hard to parse. For me, it was the main difficulty of these papers was just figure out how to contradict every single point of this definition. So you have a group mapping to G, gamma to G, G now is this. And suppose you have finite index subgroup inside gamma 0, and you have another subgroup in G containing its image, the image of gamma 0. And so now we suppose that H contains a normal subgroup which is central. And the map from gamma 0 to H quotient by A is a homomorphism, is equivalent to homomorphism. Equivalent means that it is homomorphism up to a finite bounded quantity. Then it is a constructible quasimorphism. It's called. So this is the kind of quasimorphism you can obtain from commutative. And they say that every long quasimorphism with discrete group is contactable. This is why people don't study this business. It's because everything is trivial. Not so. We found that it is won't work. To explain this, I need to do more geometry. So let's work with homogeneous quasimorphisms, which are, you just restrict the quasimorphism to its Segre group, it's a group homomorphism, which it turns out that it's a very nice notion. So every quasimorphism is equivalent to a unique homogeneous quasimorphism. I'm not going, it's a good exercise, but I will write you a formula. So to find this homogeneous quasimorphism, you take limit, you take Q of nx, divide by n and take limit. This would make sense because the difference between Q of nx and n Q of x is bounded. So if you divide that by n, it goes to 0. But uniqueness is not that obvious. And it's very nice notion. It's something you always assume having with working with quasimorphism, because quasimorphism in its equivalent class has a unique homogeneous quasimorphism. Okay, the problem is that it entirely stops working. Everything stops working when you're non-commutative. For instance, if you have a homogeneous quasimorphism in that sense, you twist it, you just conjugate it by an element of your group G. It remains homogeneous. So sort of even uniqueness is not that obvious. Anyway, I'm not claiming that it is false, but I'm claiming that it is unclear. And we try to prove it for general. So we try to establish what is known for homogeneous quasimorphism for general, or working with hyperbolic group or something, and it didn't work. It works only for Bargis, which sort of tells us that something is hidden here, but we don't know what. So element is called primitive if it can be represented as a power. So you expect that in geometric situation this should be true, because you can't expect that there are many very small geodesics. And in fact, the same is true even for Gomo hyperbolic group. So every element in the manifold of negative sectional curvature is an integer power of a primitive element, which is not power of any. You can do it as an exercise. But we used Gromov hyperbolicity for a proof. I don't know why. Okay. Now, more importantly, which is now is a statement about harmonic maps. So you have unique harmonic map from a harmonic map restricted to a in dimension one, restricted to a line. It's just a geodesic, and harmonic maps to hyperbolic manifold to negative sectional curve, which exists in unique in every homotopy type. But this is classical. So if you have a compact manifold negative sectional curvature and a primitive element of a panel group, there is a unique free geodesic loop representing this gamma. So free means that it's not connected to a point. So it's like you go from your reference point to some point on this loop, you go around and you go back. And it exists and is unique in every conjugacy class. So this is a statement about minimal loops in a geodesic space. You can think about minimal loops in things like Riemann surface, and this is something that people do a lot. There's a whole complex of these minimal free loops, and very important in low-dimensional topology. But it's always, when people speak of systoles, they mean precisely this kind of objects. Okay, so I'm thinking of the shortest free geodesic loop representing a given gamma, because they are used to define homogeneous version of Bargis quasimorphism. They're not Bargis directly, so we write abbreviation HBG, because they're homogeneous Bargis, but they're not Bargis. Okay, so I fix now for each gamma, I denote the minimal loop primitive for gamma, which is a power of primitive. I consider the minimal loop representing gamma, and I just iterated b times. This would represent me the gamma as a loop, as a free loop. And I fix a point on each minimal loop for all gamma, just fix it once and for all. This is because we want to have not free loops, we want to have a reference. So when I start with a reference point, I take a geodesic to F gamma, go along F gamma and return. And such a three-segment path representing a given gamma is unique. Of course, there are many ways to connect given X and given P by geodesics downstairs, but upstairs it's unique. And for each different way you connect it, you will have a different element of final group conjugate to gamma. And we want a particular element, so we fix this path is fixed. And clearly, since when we take a power of gamma, we just iterate gamma several times, the map holonomy along this path, so we go from P to our free loop, go along free loop several times and return. This is a quasimorph. Well, this is restricted to a cyclic group. It's a homomorphism. Okay. And now theory. We have this map. Again, it takes a base. It takes an element of an group to this 3-segment geodesic loop in your manifold, and its holonomy gives a Ulam quasimorphism, which is homogeneous. Homogeneous is clear, but the rest is not clear, and it's illustrated by a picture. Okay. Now the picture and the rest. So this is the statement. So how? Okay, you have this 3-segment. We denote by gamma the segment alpha beta minus 1. You have 3 elements, and you have this geodesic triangle. Well, you have this Q of A, Q of B, Q of A, Q of gamma. It's a holonomy of along a nonagon. Nonagon is a polygon with 9 edges. So you have this nonagon, which is formed by first these 3. So downstairs, it's like 8 pieces of geodesics, but upstairs it's actually fillable. It's homotopy to 0. And then you have a geodesic nonagon. Your defect is holonomy along this its boundary, which is very good because you can fill it, and using the theorem 1, you obtain that its holonomy is actually bounded. So this is again a quasimorphism. Slightly more complicated because you have nonagon and not triangle, but it is still a quasimorphism. Good. So this is our HBR. And the good thing about these HBRs that they can do whatever you like with them. You can write, you can prescribe values, and you can construct these quasimorphisms with any given value if you are creative with connection. They depend on connection, and you can do lots of things with connections. So before I'm going there, let me give a remark. So we're interested in non-conjugate cyclic subgroups. We want lots of them. There are infinitely many. This follows from Gromov hyperbolicity again, which I'm not going to explain. There's no time, but it's just something which sits in the background. So there's a huge class of groups called Gromov hyperbolic. Gromov has this very funny thing that if a statement is a statement about general groups, it's either true or false or vacuous. So it's probably not very well. It's sort of sacrilege in Novosibirsk, but he was not interested in general groups. But he was interested in special groups like property T, amenable, and what is most important, hyperbolic, which he invented. This is groups which, if you take its Cayley graph and you look at this graph from very far afar, it becomes a tree. And all manifolds of negative curvature, the final group is Gromov hyperbolic, but not vice versa. I think there are more Gromov hyperbolic groups, even with some finiteness conditions too. Okay. So they have lots of pairwise non-cyclic subgroups. They have lots of normal subgroups. So this is a very nice class. Okay. Now we have a manifold of strictly negative curvature. We have a collection of primitive elements generated cyclic subgroups which are non-conjugate. Then you can have a and you have collection of elements in your target group. Then there is a connection on a trivial principle G bundle, such that the corresponding quasimorphism takes your given elements, the generators of your cyclic subgroups, to your given GI. Whatever you like is doable. So for instance, if you have A, B, and AB, they are non-conjugate cyclic subgroups. So you can have A goes to something, B goes to something, and AB goes to something. This is how you obtain quasimorphisms which are not, which are very far from homomorphism. Maybe you have questions? No? Okay, so how you can prove this? The idea is very simple. So you have our elements of the group represented by loops, which go from P to our free loop and around several times along this free loop and back. So we take a very small open ball, which intersects this at given free loop and doesn't intersect the rest of free loops. We have finitely many, so we just prohibit this very small ball intersecting the rest of free loops. And we modify our connection, like trivial connection, we start with trivial connection, we modify it on this very small loop in such a way that the holonomy, so can be always done, is given, is prescribed, takes prescribed value. So this new quasimorphism, it will be the same as the old one, but it will on the rest of the generators, but it will be like trivial or non-trivial, but with the given prescribed values. But on this the new generator, which we just modified, it will take prescribed value. So this is how you can do. There's a hyperbolic counterpart to this construction, which is purely algebraic, which is, I think it's called Brooks quasimorphism. Maybe I shouldn't tell about it, but it's really fun. Questions? No? Okay. So this is how you prove, you disprove the Fujiwara-Kapoich theorem. You take your we do it with the nilpotent group. It's slightly simpler. So we take a lattice inside nilpotent group, which is co-compact, and we set our generators in such a way that the xi goes to the generators of this lattice. This prohibits taking the subgroups in this strange Kapoich-Fujiwara definition. And then we do it ingeniously in such a way that it's very far from a quasimorphism or homomorphism. Okay. Another interesting problem, which is actually more due to Ulam, it's more related to Ulam than the rest of the discourse, is Kazhdan-Milman. Well, it's Kazhdan wrote a paper in '82, which answers a question of Milman. So Kazhdan, his earliest work were on property T, which is more or less whether a given group, its trivial representation is isolated inside the space of all representations, which has a topology called field topology. So what Milman asked was more similar to what Ulam asked, is where suppose you have a quasi-representation, a map which is very close to representation. Can you approximate it by representation? So let's define epsilon representation. It's a map to unitary group. So the target in that part of is always unitary. There are two flavors of this. It's called Ulam stability. There's two flavors, strong and weak, depending on whether you allow for infinite dimensional Hilbert spaces. And then the defect is less than epsilon in operator norm, or in failure notion as well. You can do it. It doesn't really matter. And then Kazhdan asks for which groups, for any delta, there exists epsilon such that any epsilon representation can be delta approximated by representation. Now these groups are called Ulam stable. And he proved that Ulam stability is true for amenable groups. which are like commutative groups or groups slightly related to commutative, nilpotent. But it's definitely false for hyperbolic. Amenable is very far from the first amenable groups were invented by von Neumann. His first example was free group, which is very hyperbolic and very non-amenable. Okay, so he proved it for amenable, but for genus 2 Riemann surface, he has constructed epsilon representation, which can be for each epsilon, which can be approximated, even 1/10 approximated. So it had a fixed bound for approximation. And this was a very good result, but of course, it's very explicit. He has a, in fact, I think something similar was done by Gusevsky, also explicitly, slightly later. So it was in Novosibirsk. But now we have a non-explicit, very conceptual argument, which works for all negative sectional curvature bundles, negative sectional curvature matrix. So you have any positive dimensional Lie group, you have a trivial principal G bundle, you can produce HBG quasimorphism, which is very close to, as close to an epsilon representation as you can have, but cannot be approximated by representation. Okay, this is it. So the last picture of Sasha, it's he is in San Carlos. So he's when he went to Brazil, it was to Campinas. I think there was some mathematician from Novosibirsk who was already there, and he managed to attract other people to Novosibirsk, from Novosibirsk to Brazil as well. But Sasha was one of the first, and then around 2012, maybe, he moved to San Carlos, where he had several seminars. Even now, I met students who are very impressed by his teaching, which is amazing because so much time passed. And he had this seminar, Structuras Geométricas and Variedades, and this is probably after the seminar. Okay, now I'm definitely done. Thank you very much. And
thank you very much, Misha.
And I can stop sharing, I suppose, or should I? Probably I can.
Are there any questions?
Yeah.
Нет вопросов.
Матросов.
Okay. Okay.
Okay. Thank you very much,
Misha, for the very interesting talk.
Thanks.
Okay. Now it's my big pleasure to introduce our next speaker, Carolina Arayo. The title of the talk is Birational Geometry of Calabi-Yau Paris.
Hello, can you hear me?
Hello. Yes.
Hi, thank you very much. So first of all, I'd like to say that I'm very honored by the invitation. It's very good to be here, to be able to talk to you and tell you a little bit of some mathematics and in the memory of Sasha Ananьina. So I met Sasha here in Brazil. We organized together with Misha Bilolipetsky a conference in algebraic geometry and hyperbolic geometry in 2013. And then Sasha gave a very nice talk, and it was have very good memories from that week. So today I'm going to tell you about the birational geometry of a Calabi-Yau pair, of Calabi-Yau pairs, and this is a joint work with Alessio Corti and Alex Massarenti. And this is everything that I'm going to tell you today is over the complex numbers. So the idea is that, so this is a ongoing project on birational geometry. And what I would like to do today is to motivate this theory. So I would like to start by discussing automorphisms of projective varieties, and then the motivating problem comes from automorphisms of K3 surfaces. So we are going to get there. So let me just start by introducing the notation. So when you have two projective varieties X and Y, then you can talk about morphisms between them. And so this is our thinking of this as maps given by polynomials. And if you fix a projective variety, it's very natural to study the automorphism group of X. And this is a Lie group, and this is very much studied in algebraic geometry. So if, for instance, if you take the connected component of the identity, this is a complex algebraic group. And so you can divide your automorphism group in this complex algebraic part, and then the quotient is going to be a countable discrete group. So let me give you as an example. Let me look at what happens for Riemann, for compact Riemann surfaces. So if X is a smooth projective curve of genus G, we know that there is this natural trichotomy in genus 0, genus 1, and genus greater or equal than 2. So meaning positive, 0, and negative curvature. And if you look at the automorphism group of these three classes of varieties, they have different behaviors. So for instance, in genus 0, we know that the automorphism group is just the PGL2. And so we only have this complex algebraic part. And then in genus 1, you have that so we have here an elliptic curve, so it has many automorphisms. It's a product structure, so it acts in itself on itself by translations, and for genus greater or equal than 2, this automorphism group is always finite. So notice that even though in the first and the second two cases the automorphism group has a positive dimension, we are in a different situation, because for genus 0, this is actually an affine variety. This automorphism group is an affine variety, while in genus 1, this connected component of the identity is a projective variety, is the curve X itself. And now this is what is more interesting for us. I would like to discuss automorphisms of smooth hypersurfaces. So there is this, if you take X, a smooth hypersurface of degree D, then there is this classical theorem by Matsumura and Monsky that says that the automorphisms, all the automorphisms of the hypersurface, in fact, come from automorphisms of the ambient space, except in two cases: the case of n equals to 1, dimension 1 and degree 3, so this is the case of an elliptic curve, and the case of dimension 2 and degree 4, which is the case of K3 surfaces. So in this case, in the first case, the automorphism, we have already seen it, it's always infinite. And in the second case, the case of K3 surfaces, well, this depends a lot on the surface. It is what we know is that it is a discrete group, but sometimes it's infinite, sometimes it's finite. But in both cases, on the other hand, if you look at the subgroup of automorphisms that come from restrictions of an automorphism of the ambient space, then this group is finite. So the question that we are interested in is where do all these other automorphisms come from? They don't come from automorphisms of the ambient space, but we would like to use the ambient space to describe them somehow. And in order to explain how we want to do this, I need now to move to another kind of object in algebraic geometry, another way of capturing symmetry that comes from birational geometry. So birational geometry, what we are interested in is some type of classification of algebraic varieties. So let me review the classification problem in algebraic geometry. In dimension 1, usually the way that we classify compact Riemann surfaces is first we fix a discrete invariant the genus. And so this gives you a rough classification of Riemann surfaces. And once you fix then the genus, you can look at all the possible isomorphism classes of Riemann surfaces of that genus. So this is what we call usually denote by MG, the moduli space of curves of genus G. And so this means that the classification has two parts. First, we fix some discrete invariants and classify our Riemann surfaces. And then for each, we have a moduli space describing the possible structures for every fixed genus. However, in higher dimensions, the classification problem is slightly different because there are way too many isomorphisms classes. So we do not want to really classify up to isomorphism. And what we do is the following. So first of all, we will define a more coarse equivalence relation than the isomorphism. So we say that two algebraic varieties, projective varieties X and Y, are birationally equivalent when they have dense open subsets that are isomorphic. So this is equivalent to saying that I have a rational map, meromorphic map between X and Y with an inverse. And what we want to do then in algebraic geometry, the classification problem is what we call the birational classification. So the first step is, given a projective variety, we want to find a simplest representative of this in this birational class. So this is what we usually call the minimal model of the given projective variety X. And so this is the first step. And then what we hope for is to construct moduli spaces of these minimal models with some fixed discrete invariants. So this is the rough plan for birational classification in higher dimensions. So let me focus a little bit on the first part. So the first part asks, if you give me a projective variety, I want to find a simplest representative in its birational class. So this is achieved by what we call the minimal model program. So the minimal model program, at least conjecturally, tells us how to, from a projective variety X, get to a minimal model in its birational class. So in dimension 1, in fact, birational equivalence is the same as isomorphism. So this is the classification was done pretty much by Riemann. In dimension 2, this was developed by the Italian school and finished in the early 20th century. And in dimension 3, there was a lot of people working on this, and then this was really finished by the work of Mori in 1988. And that's one of the reasons why he got the Fields Medal shortly after that in 1990. And even though the full minimal non-model program is not yet known, we have a big chunk of it, which is enough for many practical purposes. And this is due to the work of Bikar, Caccini, Hakon, McKernan in 2010. Okay, so now that we, I will use a little bit of the Mori, the minimal model program later on, but now I just want to observe that if you now want to understand classification up to birational equivalence, it's important to be able to distinguish two birational classes. And so we ask which properties are invariant under birational equivalence so that I can use this to check whether two given projective varieties are birational equivalent. And the first observation is that the automorphism group is not a birational invariant, and this is very easy to see. So if here in this diagram, I assume that X and Y are two birationally equivalent varieties. If you give me a automorphism of X, so a morphism here, then I can compose it with the birational equivalence to Y, but then I do not get an automorphism of Y. I only get a birational self-map of Y. So this is why the automorphism is not a birational invariant. And then we define this other notion, the birational group of a variety. The birational group of a variety is the group of birational self-maps of X. And this is now a birational invariant, and it has been used to distinguish different birational classes. And so, for instance, it has been used many times to prove that a variety is not birational to Pn, and so on. And so this leads me to introduce a very important character of this talk, which is the Cremona group of in dimension n. So the Cremona group of Pn is the group of birational self-maps of Pn. And now let me tell you a little bit of what is known about this group. So the Cremona group of the plane has been classically studied. So this is an example. The standard quadratic transformation is the simplest example of a birational map that is not an automorphism. So this is given in coordinates by inverting the x, y, and z coordinates, or in other words, if I multiply by x, y, z, I get this quadratic transformation given by this degree 2 monomials. So this is why it's called the standard quadratic transformation. And geometrically, what this transformation does is it's outside the union of the 3 coordinate lines. It is an isomorphism, but then it contracts each of the coordinate lines to the opposite coordinate point. So this has a very interesting geometry. And there is this classical theorem of Neder and Castelnuovo that says that the Cremona group of the plane is generated by the automorphisms of P2, so the linear maps, and this standard quadratic transformation tau. So so we understand the automorphism group very well, and then we have this one involution, the quadratic the standard quadratic transformation, and with that we generate the whole group. So this group is very much studied, and you may think that just by knowing these generators you can say everything about the group, but things are not, of course, not so simple. And now let me move to higher dimensions. So in higher dimensions there is a big difference here. So this is the Neder-Castelnuovo theorem in dimension 2, and it says that you can generate the group by using elements generators of degree 1 and degree 2, and one of degree 2. Now in higher dimensions this is far from being true. So Hilda Hudson already knew this in 1927, that starting in dimension 3 the Cremona group cannot be generated by elements of bounded degree. So if any set of generators we have unbounded degree, and actually it is going to be even more uncountable. And despite this, we still do not know any nice set of generators. And so the way that we use to study the Cremona group in higher dimensions will not be based on a nice set of generators, but we have instead another tool which can be thought of a weak factorization theorem for the Cremona group, which is called the Sarkisov program. So this was first proved by Corti in dimension 3 in 1995, and the generalization to arbitrary dimension was done by Haken and McKernan in 2013. So now I would like to explain the Sarkisov program, and this is probably one of the best tools that we have in order to investigate and to describe the Cremona group in arbitrary dimension. So the Sarkisov program says the following. So if you give me any birational self-map of Pn, I can decompose it as a composition. I can write this as a composition of simpler birational maps. There is one subtlety here, is that even though we are going to decompose a birational self-map of Pn, this intermediate variety is x1 up to xn-1. Well, here the n, of course, should not be the same here. Sorry, I apologize for this. So the intermediate varieties are what we call Mori fiber spaces. So these are, to be very precise, this is so each point is not really each variety is not only a variety, but it comes with a fibration. So Pn is just mapping to a point, and that's why we usually don't see it. But each intermediate variety will be what we call a Mori fiber space. So this means that that the variety X as well as the base Y, they have a sort of mild singularities, and in the language of the minimal model program, these are terminal singularities. These fibrations, they have relative Picard rank 1, so these are sort of what we call elementary fibrations, and the anti-canonical is relatively ample. So you don't have to worry so much about this if you haven't seen it, but this may be what you should keep in mind, is that these Mori fiber spaces are precisely the possible outcomes of the minimal model program in higher dimensions, and the maps that I use to decompose my given psi are called elementary links. And again, they have a very precise definition. Instead of giving you the precise definition, I will give you just an example of what these objects are in the surface case. So in the surface case, the Mori fiber spaces are simply, there are two types. That's either P2 mapping to a point, or it's a Hilbert surface, an FM mapping to P1. So by the F0 is just P1 cross P1, and the F1 is just the usual blow up of P2 in one point. And so these are the Mori fiber spaces. These are the possible intermediate varieties that will appear in the decomposition. And the elementary links are of 4 types. So the first type is you can start with P2 mapping to a point, and then you blow up one point of P2, and then you get to F1. And then this would be type 1. The type 2, you could start with a Hirzebruch surface FM, then you can blow up one point, get to a variety that we call Z, and then on Z you can contract this strict transform of the fiber containing the point that you blew up. So you do this, and then you get to another Hirzebruch surface. This is usually called an elementary transformation for ruled surfaces. This is the called of type 2. The type 3 is just the inverse of type 1. So you are on the blow up of a point, and then you contract back the exceptional divisor to the point. And then the type 4 is something that is very specific for P1 cross P1, where you just do an involution that exchange the two factors. So you see this is very easy to justify that this should be called elementary links. These are very simple maps. And any birational map of P2, you can decompose it using the Nader-Castelnuovo theorem, or you can decompose it by elementary links. And this is sort of two different ways of working with birational maps of P2. And in higher dimensions, I'm not going to say much, but in higher dimensions, you have elementary links again of the four types, and they are sort of very easy generalizations of these 4 types. But I don't want to get into these details, but now I want to go back to the problem about the automorphisms of smooth hypersurfaces, and I am going to connect this to the Cremona group. So let me remind you the problem that we discussed. We had the smooth hypersurface of degree D in Pn+1, and by the theorem of Matsumura-Monsky that I already told you, except for dimension 1, degree 3, or dimension 2, degree 4, the automorphisms of X all come from linear automorphisms of the ambient space. And then we had these 2 exceptions, the genus 1 curve, where we understand the automorphism very well. It has a copy of C together with some finite group, or the case of a K3 surface where the automorphism group is discrete, possibly infinite, while the automorphism, in this case, the automorphism that comes from the ambient automorphism of the ambient space forms a finite group. And now we ask, where do all these other infinitely many automorphisms come from? And in the case of a genus 1 curve, the answer is very nice and very well known. So this is sort of a folklore theorem that says that every automorphism of the elliptic curve is in fact induced by a Cremona transformation of the ambient space. So it may not be, in general, it is not going to be induced by an automorphism of the curve, but it is induced by a Cremona transformation of P2. And so we have an exact sequence like this. So this group in the middle is what we call, usually is called the decomposition group of the cubic of the curve. So this is the group of Cremona transformations of P2 that stabilize the curve. And so if they stabilize the curve, they restrict to an automorphisms of C. So this is this part of the sequence, and the kernel is what we call the inertia group of the cubic. So I'm denoting it by G. So this is the group of Cremona transformations of P2 that fix the cubic pointwise. And these two groups, the decomposition group and the inertia group, have been very much studied. So for instance, in 2007, Ivan Pan gave generators for the decomposition group. And a bit later, in 2008, Jeremy Blanc gave described the generators for the inertia group. So this is by now a very classical topic. And now we want to look at the next exception, which is the case of K3 surfaces. And here, Giza-Tulin asked the following question. Is every automorphism of S induced by a Cremona transformation of P3? And the first person to address this question was Ogiso. In 2012, he wrote two very nice notes on this topic. So in the first one, he constructed an example of a quartic surface in P3 with automorphism group infinite cyclic, isomorphic to Z, but such that no non-trivial automorphism is induced by a Cremona transformation. So this answers negatively the question of Giza-Tulin. And later on, he constructed another example, which was in the opposite situation. So the group was much more complicated. It was the free product of 3 copies of Z mod 2Z. And in this case, even though the group is much more complicated, every automorphism of the surface is induced by a Cremona transformation of P3. And so after this, he raised the question, well, maybe, based on this very few examples, a natural question is that is it true that at least every finite order automorphism of a quartic K3 surface is induced by a Cremona transformation? And so he left this question, and this was answered very recently by Daniela Paiva and Ana Quedo. These are 2 PhD students of mine. They explore these tools introduced by Ogiso and construct another example of a quartic surface with automorphism group infinite dihedral. So free product of 2 copies of cyclic of order 2, but still also in this example, no non-trivial automorphism is induced by a Cremona transformation. So it seems that it's very, very wild. We do not have any nice criteria yet to say when an automorphism will be induced by a Cremona. But we have been developing tools to study this, and this is now what I want to explain to you. So if you have a K3 surface S, we want to describe the decomposition group of S. And this is, again, the group of birational transformations of P3 that stabilize the surface. And also we want to understand the image of the decomposition group in the group of automorphism of X. And the question of Giza-Tulin was, when is this surjective? And now P3 together with the K3 surface is what we call the Calabi-Yau pair. And so the tools that we have been developing are more general, and they can be used to study birational geometry of Calabi-Yau pairs in general. So let me introduce this formally. So a Calabi-Yau pair is a projective variety X with mild singularities, to be very precise, with terminal singularities, together with a hypersurface D that is anti-canonical, and such that the pair XD is log canonical. So we also impose some restrictions on the singularities of the pair. But the typical example that you can think of is, for instance, when X is Pn and D is a smooth hypersurface of degree n+1. So this is the prototype that you should keep in mind. And whenever you have a Calabi-Yau pair, there is a unique up to scaling meromorphic form of top degree, such that the divisor of this meromorphic form is exactly minus this. So what this is saying is that whenever you give me a Calabi-Yau pair, I know that there is a unique up to scaling meromorphic volume form that does not vanish in codimension 1, and it has a simple pole along D. And now we will always have this this meromorphic volume form in the back of our heads. And now we can define a notion, a morphism in this category. So a morphism in the category of Calabi-Yau pairs is what we call a volume preserving birational map. So what we start with any birational map between X and Y. And so when we have a birational map, we can identify their meromorphic volume forms. It induces an identification in the set of meromorphic volume forms. And we say that a birational map is volume preserving if this identification takes the volume form associated to one divisor with the volume form associated to the other divisor. So this is what we call a volume preserving. And now, now another problem. So I told you about understanding the composition. If you give me a Calabi-Yau pair, I can ask what is the birational group of the pair, meaning the group of birational transformations of the ambient space that is volume preserving with respect to D. So this is okay. So this is the problem that we have been investigating and developing tools to understand. And let me compare it with the previous problem that I explained to you. So if from Giza Tulling's question, we were interested in understanding the composition group of a quartic K3 surfaces. So this was the group of birational transformations of P3 that stabilize the quartic. And it turns out that this is precisely the same as this volume preserving condition for a smooth K3 surface. And so understanding the decomposition group now will become understanding this birational group of the pair, the group of the volume preserving birational maps. And this is true in more general whenever the pair has canonical singularities, then the composition group, which is the group of birational maps that stabilize the hypersurface, is the same thing as the group. Yes. Okay. Is there any question?
No questions.
Okay. So under this condition that the pair has only canonical singularities, and for instance, in case of P3, of a surface in P3, this is just double points or Duval singularities. Then understanding the composition group is the same thing as understanding the birational group. But the good thing is that for the birational group, we have much more tools. But before I explain this, let me just say that the canonicity here, this restriction on the singularities is necessary. And this is just, I have an example to illustrate this. So if you start with P2 with the 3 coordinate lines, and then here the meromorphic volume form associated to this is this one written in affine coordinates dx over dx over x, wedge dy over y. So in this case, the standard quadratic Cremona transformation clearly will preserve this volume form, but it does not induce a birational map of the triangle, so it contracts. So it is, in this case, this is not in the decomposition group, but it is in the birational group. So this is just to illustrate that the problem here is that we had the hypersurface here is not normal. So in this case, this is what makes it this fail. And so, as I said, now that we know that at least in our case, the decomposition group is the same as the birational group, we have many more tools coming from birational geometry to study this problem. And let me state this in a sort of a vague way. Let me just say that there is this theorem of Carty and Kalogiros from 2016. They proved that any volume preserving birational map between two Calabi-Yau pairs in Pn they can be written as a composition of volume-preserving Sarkisov links. So the Sarkisov links are exactly the same ones that I explained before. And the question of volume-preserving just means that on each of these intermediate varieties, I can put a divisor such that it is a Calabi-Yau pair, and this is a volume-preserving map. So using these tools, we started to investigate this problem of given a Calabi-Yau pair to determine the birational group of the pair. And so today I just want to state two theorems that we proved about this. So the first one, by using the volume-preserving Sarkisov program, we could prove that if the hypersurface is general, so if, again, we have a general hypersurface of degree n+1 in Pn, then the group of birational maps of the pair is just the automorphism group of Pn with D. So in a sense, this is saying that there's no really any interesting birational self-maps of Pn with respect to this general hypersurface D. So by general here, I should say that I mean that it is smooth and it satisfies sort of the Lefschetz property that the Picard rank of D is equal to the Picard rank of the projective space, which is 1. So under this case, we cannot produce any interesting birational map. So if you want to now use this tools to produce say by subgroups of the Cremona group, you will have to get rid of this generality assumption. So there are two ways to proceed. Either you can take a special hypersurface, a smooth hypersurface, but with a bigger Picard group. For instance, for K3 surfaces, this is the examples constructed by Ogiso. So this is actually really for the examples that I explained before. You get some interesting subgroups of the Cremona group, of the inertia group of certain smooth K3 surfaces, or you can go in a different direction and allow for singularities in your hypersurface. And this is what we did, and this is our theorem B. We consider a quartic surface, but now instead of taking it completely generic, we allow it to have one singular point. So we call this singular point P, and then we take a general quartic hypersurface with this singular point. And now we get some interesting subgroup of the Cremona group. We are able to compute the birational group of this pair, and it has a very interesting structure. So it can be written as a semi-direct product of G with a cyclic of order 2. So this G here is a form of GM over this function field of the plane. So what this means is that this G here is an algebraic group over the function field of P2 CXY, such that when you take the closure, the algebraic over the algebraic closure of this field, this becomes GM. So this is what we call a form of GM. But this is not really only a abstract theorem. In fact, we compute this group G very explicitly. So let me just explain this. So if you give me the equation of the quartic, so with one singular point, if I take this singular point to be 1, 0, 0, 0, then this is the equation of a quartic with the singular point. So this is a quadratic, a degree 3 and a degree 4 polynomial. So in this case here, the point, well, this green cone is just representing the tangent cone to the quartic at the singular point, and it's given by this degree 2 equation here. And so if the quartic is given explicitly by this equation, then we can actually describe this group G, the form of GM is just, I give you all the birational maps in this way. So you fix any f and g, any homogeneous polynomials with this degree condition, and then I plug them in this formula, and I get a Cremona transformation of P3 that stabilizes this quartic surface. And so this is actually all that I wanted to prove both theorem A and theorem B. What we do is a very delicate analysis of using the volume preserving Sarkisov program. So I thank you very much for your attention.
Thank you very much, Carolina, for your very interesting talk. So, are there any questions?
So maybe I have a couple of questions of similar type. So what happens, first of all, do you have the relative version of this? So when you have your Calabi-Yau pair over some base. And the second one is when you fix your, say, projective space and you prove something for general hypersurfaces. And what happens if we vary? So if we have degenerate, is the group jumps or the other way around?
Yes, so thank you for the questions. Let me maybe go back here to, so the volume preserving Sarkisov program. So here I put a PN, but I could put any Mori fibered Calabi-Yau pair. So the theorem is for, in general, for Mori fiber spaces with the additional structure of a Calabi-Yau pair, and the full theorem is the same. The theorem is the same. And even if you start with PN already in the first, usually in the first step, you get to a proper fibration. And usually here you will start, say, by blowing up or doing a weighted blow up of a point, and then in the end you get to a fibration. So this theorem is very, very general. And for your other question, so maybe here I put the theorem A. So in general, if you take a special hypersurface, the birational group is going to jump. It's going to, in general, get bigger. So here you say, if you take something, for instance, in this case, if you had the smooth for K3s, you had the smooth with Picard number 1, then there's just the automorphism. And then here you allow for one singular point, one singularity of type A1. And this is what I mean by a general surface with one singular point, you get a singularity of type A1. And then the group becomes much bigger. And actually, we started to investigate also the possibility of one singular point of type A2. And in this case, you get at least this big birational group, but there is still room for more. But we have not yet so far been able to determine if you actually get more interesting birational groups. But in general, if you specialize it, it tends to jump.
So you expect that it's stratified, yeah, for general something, for in some dimension, some more group, bigger group, then inside dimension inside this set, some even more bigger group, and so on.
Yes, yes. I mean, we have not formalized this, but this is what the examples show us.
Thank you.
Okay. Are there any other questions? No. Okay, thank you very much, Carolina, again. Okay, let me introduce our last speaker today, Dmitry Korshunov.
Everybody can hear me?
Yes, we hear you.
And do you see me?
No, unfortunately not.
You're black.
Wow. Just a second. I'm gonna need a minute. Ah, okay. Oh, yeah, that was easy.
Now it is okay.
Okay, so I needed to share a screen.
It looks like you're in some museum.
Yeah, sort of. Okay. here we go. Do you see? Can you see
Yes,
the slides,
but
right?
please, now it is okay.
So you see slides, right? Okay.
Yes. Yes.
So hello, everybody. Thank you for having me here. Today I'm going to talk about the work we've done with Sasha during the last months of his life, literally, and I believe that it is like very characteristic. So the work is very characteristic of him because like some of the key objects that we used in the proof popped up in Sasha's work even when he was an algebraist. So here's an archive link. It's on archive, and it's about isometric deformations of polyhedral surfaces in R3 and its and its relations with Kapovich-Milson space of polygons. Okay, so some definitions first. The main object is modular space of polygons. So a spatial polygon is a sequence of vectors in R3 with some fixed length that sum up to 0. So here's example of two different realizations of the same polygon. So as a space, as a geometric space, it's an algebraic space. It can be considered as a subset of the product of n spheres of radii, of fixed radii, subject to 3 linear conditions, namely linear conditions that the sequence of vectors sums up to 0. And yeah, and we want to consider two polygons as the same if they're related by an action of an isometry group of R3. So we want to identify that. And this modulus, so we will call it modular space of polygons, and it exists. And and this is a theorem due to Kletchko and Kapovich and Milson. And the construction is basically a symplectic reduction. Okay, so I'll give one more definition. It's the risky tangent space and infinitesimal deformation of a polygon. So the risky tangent space is just a linearization of some system of algebraic equations, and if we differentiate the algebraic equations defining our modular space of polygons, then we get this condition 2 that describes that tangent space, the risky tangent space to a polygon. And there are always trivial infinitesimal deformations, namely trivial tangent vectors to a polygon that come from infinitesimal deformations of an ambient space of R3. And we don't want them. We want to quotient them out. Okay, so now I want to describe the symplectic structure on the modular space of polygons. This is like sort of miracle, and this is like the main structure we are going to use. So first of all, the sphere has a symplectic structure, and it is described by this formula. So if we have two tangent vectors, we can take a symplectic form of it, weighted by the radius of the sphere. And for a sphere, there is symplectic reduction given by sorry, the moment map. So once we have a Hamiltonian action of some group on a symplectic manifold, if this action is good enough, if it is Hamiltonian, then there is a symplectic, then there's a moment map. Namely, it's a map from a manifold to the dual of the Lie algebra of the Lie group acting on the space, and the map in this slide, basically when we have a point on a sphere with the sphere standard embedding in R3, and when we take this point as a vector in R3, and R3 is naturally identified with dual to Lie algebra of SO3, and this map is the moment map. Okay, and like there's a general theorem of symplectic geometry that once we have a moment map, that we have a Hamiltonian action with moment map, then we can quotient level surfaces of moment maps by the action of the group. So this allows like to do a reduction, as what's called symplectic reduction. Okay, so we have a symplectic structure and the moment map for the standard action of SO3 on a sphere. Also, SO3 acts on a product of spheres diagonally, and the sum of moment maps for each sphere is a moment map for this action. And again, since the moment map for a sphere just like tautological map, so for a point we take this point as a vector, the moment map for the diagonal action of SO3 on a product of spheres will be the sum of corresponding vectors. And this, like, sort of miraculously, this is exactly the sum of vectors, and the zero of this moment map, namely it's a condition, then the sum of vectors is 0, is exactly our condition for our space of polygons. And this is this allows us to construct a symplectic structure on the space of polygons. Yeah, so I just repeat like the general statement of what symplectic reduction is. So suppose we have a moment map. It's just a map from a symplectic manifold with an action of a Lie group to the dual Lie algebra of a Lie group, which satisfies a sequence of good properties, which are satisfied for our in our case. Then the orbit of the action of a Lie group coincides with the kernel of the level set, or say in 0, like in our case, of the moment map. So, like, again, okay, and this is and this is what's called symplectic quotient. We can give an explicit formula in our case. So if we have a polygon and we have two tangent vectors, two Zariski tangent vectors to the space of polygons at this polygon, namely Ti and T prime I, then what we should do is just we need to take a triple product of those two vectors with the corresponding with this corresponding vector in the check. So again, the polygon is a sequence of vectors that sum up to 0, and the tangent vectors are assignment to any vector of some vector, another vector in R3 that is orthogonal to this vector Vi, and the only condition is that they must also sum up to 0. And if we take like the triple product and divide by the volume form, it will be a symplectic form, the same as obtained by symplectic reduction. Actually, what we did in the paper is that we had very vague idea of symplectic reduction when we were writing that down, and actually we computed everything by hand, and in a sense it was like okay, because our computation worked even at the singular points, because actually the variety of polygons, it has singular points where the risky tangent space has dimension greater than expected, but this form is also non-degenerate, and so it's also symplectic form even at singular points. Okay, so like the second main object is a polyhedra and the space of polyhedra. They're defined exactly the same. So like formally polyhedron is a triangulated surface with boundary in our case, with prescribed lengths of edges. And we consider the space of all isometric realizations of a given polyhedron in R3, namely all the maps from this triangulated surface, preserving the lengths, preserving all the distances. So in general, the polyhedron with boundaries are quite flexible. So contrary to the case of closed polyhedra, which are generally not flexible, even though sometimes they are the polyhedra with boundary are usually flexible. Namely, there exist different maps preserving distances that are not related by the ambient isometry, by the isometry of R3. Okay, and exactly as in the case of polygons, we can consider the modular space of polyhedra. So formally, it's just an assignment, like for any edge, for any edge, we take some vector in R3 such that the length of all edges are prescribed. It's L, E, I, and such that any closed path of edges sum up to 0. So we want it to be consistent. And again, the space of polyhedra is defined by a sequence of algebraic equations. So it's in 3 E variables, because we, like, to any edge we assign a vector in R3, and there are like some linear conditions and some quadratic conditions. So this is a affine real manifold, as a affine real variety, a affine real scheme, and this is like important, and that was like what Sasha convinced me to do all the time, to write this, like pedantically write that this is a scheme, not a variety. And this actually has some like conceptual, there's some conceptual importance in that, because in general this set really can contain nilpotents, and those nilpotents have like geometric meaning. There are, for example, rigid polyhedra who are infinitesimally non-rigid, and this is exactly the manifestation of nilpotence of the scheme. And this cannot happen in the case of polygons. Okay, so again we have the risky tangent space to the space of polyhedra that they're defined exactly like verbatim like polygons. So here are given by a system of linear equations 4. So again, so we just assign to any edge, we assign a vector which is orthogonal to this edge, and we want those tangent vectors to sum up to 0 for any closed path. Again, as in the case of polygons, there are trivial infinitesimal deformations which we don't want, namely those that come from isometries of R3 of ambient space. Yeah, and we can quotient out by the action of SO3, namely for like we cannot, of course, apply like any reduction like GIT or symplectic reduction, like apparently, at least I don't know how to do that, but we can naively quotient it like that. So we have like at least one non-degenerate triangle, and we can fix it. So we can just assign that this triangle does not move. So that's like any infinitesimal deformation or any like real deformation is like 0 on this triangle. And this is an algebraic condition, and it actually it kills all the parasitic solutions. So we have our space, modular space of polyhedra. It's an affine scheme, and apparently it has very little structure. So besides being an affine scheme, something defined by algebraic equations, there's very little structure, and everything is very difficult there. So there is a big area of mathematics where people study the properties of this scheme, like people like Sabitov and Gaifulin. They study like even questions about the dimension of the scheme, whether it's like 0-dimensional or not, are generally very difficult. Yeah, but what we did with Sasha is that we sort of like probed. We used a natural correspondence between the complicated space of polyhedra, modular space of polyhedra with little structure, and the very structured space of polygons, which is like the Kapovich-Milson space of polygons, which has symplectic structure, which has Kähler structure, like a lot of structure. And the key object is a boundary map delta, what we call. So like its strict definition is quite boring. It's in the paper, but intuitively it is very easy. So namely, if we have a polyhedron, isometric realization of a polyhedron in R3, then we can take its boundary. We can forget about polyhedron and take its boundary, and its boundary is polygon. So there is a and this map evidently it is equivariant with respect to the action of SO3 of isometry group. So so we can, so this is like forgetful map. So we take a boundary of a polyhedron. It gives a natural map from the modular space of polyhedra to the modular space of polygons, and this induces like differential map on the risky tangent spaces, and we can ask like a bunch of questions about the properties of this map. For example, we can take a pullback of a form on the Kapovich-Milson space. So down there on the space of polygons, we can take a form, the symplectic form of Kapovich-Milson, and we can take its pullback to the modular space of polyhedra, and ask the question, how does it look? Okay, so here's this definition, but actually it's like sort of statement that how the differential of the delta map looks, and it's very simple. It's just a restriction. So if we have an infinitesimal deformation of a polyhedron, it gives an infinitesimal deformation of its boundary of a polygon, and this is exactly the differential of delta. And I can say the main theorem now namely that the pullback of the symplectic form of Kapovich-Milson on the space of polygons is 0. So namely that the image of delta is an isotropic subvariety of the space of polygons. And another part of the theorem is that actually it's if the polygon, if the topological type of the polygon is that of a disk, and it is generic enough, because like for non-generic it is not true, this map is also co-isotropic, namely that the image of this map is a co-isotropic. So for a generic polyhedral disk, the space of, so its boundary sweeps out a Lagrangian subset in the space of Kapovich-Milson. Like one have to be careful about like using the terminology of Lagrangian, because of course the image of delta is not a submanifold. At least I cannot prove this generally a submanifold. Maybe it is. It is some semi-algebraic set, and when I say that it's Lagrangian, like isotropic, coisotropic, I mean that it contains an open, dense set which is Lagrangian submanifold. Okay, so and there was like some like interesting corollaries with of this property of isotropicity, for example, is that the space that can be swept out by a given polyhedron in the Kapovich-Milson space, it has at dimension at most half of Kapovich-Milson space. So it cannot be very, it cannot be big, and we use that to prove or to disprove a conjecture of Richard Kenyon about like in combinatorial geometry. So we proved that the example that he wanted almost never exists. Okay, so like a couple of words about the proof. I don't have much time, and I want to say that in the proof of isotropy of delta, it was like Sasha's idea and the objects that he introduced, which allowed it to prove it. So the proof goes by induction. So the object is a graph, what we call graph surface. What it is? So suppose we have a closed surface, and we have a like embedded finite simplicial complex whose complement is a disk. So generally it looks something like that. So it can contain some triangles and some boundary graphs. And this object, it sort of interpolates between graphs and triangulated surfaces with boundary. Graph surface, like everything I told about modular space of polyhedra makes sense for those graph surfaces. Like it has a notion of boundary. So since the complement is a disk, it induces like a boundary which is like formally a sequence of edges, such that some edge can appear twice with opposite directions. So like again, so this is like sort of not very so it is quite intuitive, but it's not straightforward to give like strict definition. So there in the paper, but this picture is I think the best that I can say now. Okay, so here's another example of a graph surface. So it has one triangle, like many edges, and its boundary is described by the red line. Yeah, and graph surfaces, it is sort of like object that is a common generalization of a surface with boundary, triangulated surface with boundary, and the graph. So on two ends, on first end there's a graph, and here's example of a graph and the corresponding boundary. And the main step in the proof is induction. So namely for a graph surface, there's a notion of collapse. Namely, if we have some triangle which has a boundary edge, we can collapse it. So we can just delete this edge. So here it is described. So like we have some graph surface, and we have a boundary edge E3. We pick this edge and we delete it. And the induction step is we prove that if the statement of the theorem is true for a collapse, for the collapsed surface, then it is true for the original surface. And since any surface can be collapsed to a graph, namely, so suppose we have a polyhedron, and we just collapse one by one all the boundary triangles, we get a graph. And for graphs, the theorem is true. It can be checked by hand, because if we write the formula, if we write the formula for the pullback of our symplectic form, then for a graph, like everything cancels out, because any edge appears with its opposite. And in the case of if the surface is orientable, then it is. So for graphs, it can be checked by hand. So like induction goes like that. Well, okay, so I'll say a couple of words about the induction. So we have our symplectic form defined by the formula, defined by this formula. And how come that the statement for the statement of the theorem for a collapse of the zero of this form for the collapse surface implies it is zero for original surface? Okay, so actually what's going on is that the collapse surface, it is more flexible generally. So its dimension, the dimension of its infinitesimal deformation space is bigger, and the space of uncollapsed surface actually embeds to the space of collapsed surface, and this embedding is symplectic. This embedding is symplectic, and so what's going on is that we have like a sequence of symplectic embeddings of spaces of symplectic spaces with the biggest one Lagrangian and isotropic. And so like this, sorry, yeah, so the collapse gives an embedding of a modular space of polyhedron, at least infinitesimally, to the modular space of a collapse polyhedron, and which commutes with the boundary map delta. So since the biggest, like, the theorem holds for the largest space, that means that the delta is isotropic for the space we started with. Okay. Yeah, so I'm not going to tell about the proof of coisotropy of delta, because it is like discounting of dimension. So we prove that the image is isotropic, and we need to prove that it is not smaller than, so it's the dimension of the image is not smaller than half. And this holds only if the topological type of our polyhedron is that of a disk, because if its genus is higher, then generally the image of delta is smaller. So the higher the genus, the smaller the dimension of the image of delta. And again, we need like genericity condition, because there exist polyhedra with boundaries that are rigid, that cannot be deformed. Okay, so, and what about the application, about an application? So there was a problem of Richard Kenyon, which says, who asked following, like, let's call a polygonal path in R3 an integral curve. It is if it is composed of edges of length 1. So we have a closed polygon with every edge of length 1. And he asked if you can always span an integral curve by a dome. A dome is a triangulated surface. Composed of triangles of edge length 1. So it's like equilateral triangle with all edges of length 1. So the question is, if there exists a polyhedron composed of triangles of edge length 1 that spans, whose boundary is a given polygonal path, and our theorem implies that it is almost never exists. So for the majority of integral curves, they cannot be spanned. Why it is so? So suppose we have, so this is like a non-constructive proof. So given a dome, given a surface with boundary composed of triangles of side length 1, the space of all integral curves that is bounded by this dome is an isotropic subset. In particular, it has measure 0 because its dimension is quite small. It's at most half the dimension of the space of all integral curves. Okay, we have a measure 0 set, but all possible domes constitute a set of a countable set, because a dome is defined by its combinatorial structure only, because the length of its edges are always 1, so there are countably many domes. So all integral curves that are spanned by all domes is a union of measure 0 sets, so it has measure 0. So that means that the set of the unspannable integral curves make up a full measure set in the Popovich-Milson space. And like on the other hand, Pak and Glazirian proved that the space of spannable integral curves is dense. So it is like our theorem proves it is like measure 0, and Pak and Glazirian theorem proves that it is dense. So this is an application. So I think I'm done with this time.
Okay, thank you very
Are
much.
there any
Dmitry.
questions? Thank you.
Are there any questions?
Okay.
Okay, no questions.
Mm-hmm.
Thank you very
Thank
much
you.
again. Dear colleagues and friends, thank you very much for the participation of our conference. Tomorrow we will have a second day of the conference, offline conference. It will be in Sobolev Institute of Mathematics. And I hope next year we will continue our series of conferences dedicated to the memory of Sasha Ananyin. Okay, thank you. Bye-bye.
Bye.
Goodbye.